The South Atlantic Anomaly grows teeth. Operators had a nickname long before papers caught up: the bite. Cross the South Atlantic near local afternoon and you felt it. Bits flipped, detectors spiked, software dropped to safe mode and held its breath. That was the ritual. What changed was how often the ritual failed to keep pace. The weak patch has a proper name, the South Atlantic Anomaly, and it sits where the inner Van Allen belt sags closest to Earth, in that.
SAG, high-energy protons, dip low enough to sandblast electronics that anywhere else would be fine. For years, teams drew a box on a map, powered down touchy instruments, skimmed through, then brought everything back up and hoped the counters behaved. But in the mid-2010s, the edges started to creep. ESA's swarm satellites traced the field's intensity orbit after orbit, building a decade of receipts. By 2025, the weak region had expanded by an area nearly half the size of continental Europe compared to 2014. And, crucially, since 2020, a lobe southwest of Africa was weakening faster than the rest. A micro story. An imager over Brazil watched its schedule turn to Swiss cheese. The off window stretched then split as that African lobe deepened. 2 daily gaps became 3, sometimes 4, depending on orbital precession. A client asked why deliveries kept slipping. The ops lead tried to brief radiation like weather. The client heard delay. Hubble's cautious rules stayed cautious. Earth observers ran scripts. Cross the box, check particle counts, downshift if thresholds pop. CubeSats took the hit with thinner armor. Across fleets, single event upsets accumulated. Not catastrophic for any one bird, constant across the constellation. Hardened parts, ECC memory, watchdog timers, selective shielding, they all help. But every gram costs delta V. Every millimeter of aluminum steals power margin. You choreograph risk instead. Off here, on there, sprint when clear, sleep through the bite. Here's why growth matters beyond nuisance. If the weak zone broadens, more orbits intersect it, and for longer. Duty cycles shrink. That means lost images, deferred downlinks, and tighter onboard storage. As the minimum deepens, particle flux climbs. Even with care, the upset rate trends up. Lifetime shaved down not from a single storm, but from background abrasion. What nobody knew when Swarm first flagged the expansion was whether the split hinted by earlier NASA visuals would stick. Mid-2020's analyses said yes. The West African lobe slide quickened. The worst box moved. A rule written in 2018 was wrong in 2023, and wrong by more in 2025. Fixes weren't press releases. They were patches pushed to dozens of spacecraft, each with quirks baked at birth. Parallel action. Insurers watch claims evolve from isolated anomaly to recurring environment-driven upset. Premiums shifted. Reinsurers priced constellation exposure during solar maxima layered over SAA minutes. Procurement followed. Designers assumed more time per day inside higher flux, nudging choices toward rad-hard parts with longer lead times and budgets to match. A headache born in the core, mediated by physics, no clean room can control. Second micro story. A small-sat team launched on commercial-grade memory to hit a window. They modeled exposure with a 2016 map. 6 months later, logs showed triple the expected scrubs over Africa. They raised thresholds to limp along. Dynamic range suffered. Streaks crept into dawn scenes. The pictures told a story no memo could soften. It wasn't all weakening. Swarm saw strengthening over Siberia, even as a strong Canadian patch shrank. The field is patchwork, strong here, soft there. Satellites don't average a planet, they live their orbits. If your inclination spends more minutes over the South Atlantic, you inherit its temperament. On the ground, people didn't feel protons. Phones didn't crash because of the SAA. But the weather app might have missed a pass. A daily image skipped a rectangle over ocean. Quiet erosion, paid by engineers who set alarms for a box that won't stay still. This was the moment operators stopped calling the SAA an annoyance and started calling it a constraint. It's proof that regional weakening isn't academic. It's schedule, risk, and cost. One patch already messes with hardware. If it spreads further, choreography tightens and margins thin. Meanwhile, a subtler cost rose: attention. Ops teams rewrote masks quarterly, then monthly. Students flying CubeSats learned hard lessons in real time. Vendors updated radiation curves mid-contract. Insurers adjusted deductibles after reading anomaly logs like tickers. All of it sits downstream of a shield that's breathing off rhythm. Here's the line that lands. The anomaly didn't punch a hole in the sky. It lowered the ceiling over a busy lane. Every pass under that ceiling is now a choice. Collect less, risk more, or spend to survive. That choice repeats thousands of times a day, and the bill arrives quietly, in minutes you didn't plan to lose. The wandering poles, faster than we planned for. While satellites tiptoed through the bite, the compass rose itself kept sliding across the map. The North Magnetic Pole used to loiter around the Canadian Arctic. Then in the 200s, it bolted, accelerating to roughly 55 kilometers per year, arcing across the top of the world towards Siberia. Over the past few years, it eased to around 35 kilometers per year, still fast enough to outpace. Paperwork and push procedures over thresholds that cost real money. Here's what that means when you hold a device. Your phone's heading isn't a simple magnet. It blends GPS timing, gyros, and a magnetic model, the world magnetic model, that turns true north and magnetic north into the same language. When the pole moves quickly, declination shifts faster than static charts can tolerate. That isn't a dramatic cockpit moment by itself. It's drift that turns into detours, recalibrations, and errors that accumulate on busy days when the sky is already noisy. Action looked bureaucratic, which is another way of saying expensive. In 2019, authorities pushed an out-of-cycle world magnetic model refresh because pole drift was pushing predictions out of spec. Then, in December 2024, NOAA and the British Geological Survey released WMM 2025, tightening the forecast and nudging millions of devices to update. Under the hood, it's spherical harmonics and data assimilation. On your screen, it's a patch. On the ramp, it's new paint. When magnetic headings cross a 10-degree boundary, runway designations change. 16 becomes 17, cascading into approach plates, FMS databases, signage, and training. Multiply that across airports, and the just paint joke dies fast. Meanwhile, Swarm kept showing the field's patchwork, strengthening over Siberia, while a strong Canadian patch shrank. The pole chases gradients like a marble rolling across a tilted table, leaving the Canadian lobes pull and drifting toward the Siberian one. Elegant in a model, messy in operations. The practical effect is a shifting reference that tests how quickly we can keep navigational truth synchronized across cockpits, bridges, and phones. Micro-story. A harbor pilot off Greenland carried a dog-eared card with declination notes scribbled each spring. For years, the numbers ticked gently. Then they started leaping half a degree. A degree. He stopped trusting last year's card and checked the agency portal every week. One foggy morning, he caught a junior officer lining up an approach with an old chart. No lecture, just a steady hand on the wheel and a quiet reminder. The model is not a suggestion. Phones mask drift with software, but edge cases bleed through. Survey crews at high latitudes chasing baselines that won't sit still. Compasses behaving skittish when calibration lags. Military planners widening uncertainty bands near the pole. In aviation, runway renumberings have become a steady drumbeat. Training departments update memory items and sims to handle changes landing mid-cycle. Dispatchers fold WMM dates into the same calendars they use for IRAC cycles and nav database pushes. What nobody knew when the sprint started was how long the fast phase would last. The recent slowdown to about 35 kilometers per year isn't an all clear, it's a different slope. Even at that pace, forecasts degrade within a couple of years without fresh data. That's why WMM 2025 matters. It resets baselines, so compasses and guidance stay inside tight tolerances. For critical systems, acceptable error is a narrow door. Parallel action. Logistics teams learn the knock-ons. A runway number isn't just paint. It's thousands of references across JEP charts, NODAMs, databases, and training slides. Each change consumes attention, the scarcest safety resource we own. When the pole wanders faster, that tax arrives more often, and it lands during the same weeks hurricanes, blizzards, and space weather demand focus. And it's not just the north. The South Magnetic Pole meanders too, quieter in headlines because fewer people fly and sail near it, but still part of the same machine.
The two-pole story reminds you that geometry shifts are global, even when impacts feel local. A ship in the Southern Ocean, a plane in Nunavut, a survey crew in Lapland, each experiences the same field as a different puzzle. Here's the line that ties it back to the bite. The flows that tug the pole are the flows that sculpt weak patches. If the pole's path forces model updates and runway paint, those same subsurface gears are also lowering the ceiling over the South Atlantic. Navigation must sprint to keep headings honest. Satellites must duck to keep sensors alive. It's one system seen from two altitudes.
Another micro story. A regional airline safety chief built a tiny ritual into pre-flight. Verify the magnetic variation on the FMS against the fresh WMM value when operating above 60 degrees north. It added 20 seconds to a checklist. A month later, a crew caught a half-degree missync that would have grown into a bigger discrepancy on a day with crosswinds and low ceilings. No drama, just weight shaved off a stack of risks. So the wandering poles aren't trivia. They're the quiet metronome behind a lot of routine work. Keep models tight, paint when thresholds cross, brief the drift like weather, because the machine underneath, hot metal, rotation, and feedback, doesn't keep time for us. It keeps time for itself, and when it's rhythm. Shifts, we either move with it or let errors pile up until a storm day cashes them in. How the geodynamo breathes and trips. To see the shield we live under, you have to look into a river you'll never see. 2,900 kilometers down, the outer core is a global ocean of molten iron alloys. It moves, not like boiling soup, more like a dense, disciplined storm. Jets, eddies, and slow spirals form where heat escapes unevenly through the core mantle boundary. Motion in a conductor makes electrical currents. Those currents make magnetic fields. Those fields push back on the flow that made them. That loop is the geodynamo, and it doesn't tick like a clock, it breathes. The breath starts at the boundary. Rock above the core isn't uniform. Subducted slabs chill some regions, deep plumes warm others. Where heat leaves faster, convection strengthens. Where it leaves slower, flow slackens. Add Earth's rotation, and you get tall, column-like circulations, Taylor columns, aligned roughly with the axis. They bundle magnetic flux into lobes that drift, split, and rejoin. Strong lobes help lock in a tidy dipole. When the balance shifts, geometry changes. Poles wander, regional weak spots grow, and the neat dipole frays toward a messier multipolar pattern. We can't build an Earth, but we can cheat. In labs, researchers spin tanks of liquid sodium or gallium, seed tiny fields, and watch instabilities flicker. Columns split, jets precess, patches of field wander, weaken, then pulse back. In supercomputers, numerical dynamos push the physics deeper. Nudge the heat pattern at the top a few percent, and the model's field reorganizes. Flux lobes migrate, polar caps reshape, and in some runs, the dipole collapses before a new dipole emerges with opposite polarity. Those aren't prophecies, they're maps of what's possible when the engine's inputs change. Now connect that to the blink we heard from the inner core. It's solid, it grows by freezing at its top, and growth releases light elements into the liquid above, buoyancy fuel. If the inner core's rotation relative to the mantle slows, or even backtracks slightly, the shear at that boundary shifts. Freezing and melting zones adjust. A 2025 result added something bolder. Annual scale variability in the inner core's near-surface structure. Speed changed, texture changed. That means the fuel lines feeding the outer core's flow can modulate faster than we assumed. Year to decade, not only century. Earth's rotation joins the dance. Tiny length of day wiggles, milliseconds, are fingerprints of angular momentum trading places between fluid core and solid shell. When those wiggles line up with seismology's story, modelers get braver about coupling. The system has gears. None of this draws a straight line from inner core stutter to your compass today, because the mantle's uneven heat flux filters and delays signals. But filters don't erase. They smooth jolts into swells that reach the surface as pole wander here and a soft patch there. Stakes land in the patchwork. The South Atlantic Anomaly looks like flux lobe rebalancing, field lines bowing low enough to let trapped protons dip into satellite lanes. Over Siberia, strengthening suggests a counterweight. That chessboard is exactly what simulations predict when boundary heat shifts or coupling changes. Not weak everywhere, but strong and soft squares migrating across the board.
Action for people shows up as design choices. Operators don't manage a global average. They manage the square their orbit, runway, or pipeline lives on. If the dynamo breathes deeper, longer weak patches, faster drift. Satellite teams add error-correcting memory, latch-up protection, and selective shielding, then choreograph safe mode naps through hotter zones. Grid operators install magnetometers and GIC sensors at substations. Tie them to procedures with thresholds. Block automatic switching, hold voltage, bring extra spinning reserve online. Aviation tightens polar protocols. Pre-brief HF fade risk. Plan detours. Update models on schedule so headings don't surprise anyone on short final. History sets the tempo. Full reversals in rock take thousands of years. Excursions, the near flips, compress stress into centuries and sometimes sharper surges inside that. Neither is a Tuesday surprise, but both say the engine likes to reorganize when thresholds are crossed. And thresholds don't announce themselves with a headline. A few more watts per square meter of heat outflow here, a slight shear change there, and a tidy dipole sags into a patchwork that lets routine storms punch above their weight. Impact looks like quiet costs before big nights. More spares for big transformers that take months to build. More frequent world magnetic model updates and training that assumes headings won't sit still. Extra kilograms of shielding that steal propellant margin. On storm weeks, the bill comes due. GPS accuracy bands swell at bad hours. Satellite duty cycles shrink. Grid operators shed load to avoid cooking steel. Airlines detour. None of that requires a flip. A.
Wobble is enough. There's one problem planners hate. The line between breathing and tripping is blurry in real time. By the time you know a threshold got crossed, you're already writing the after-action report. That's why the right posture is weather style. Forecast, thresholds, drills, dashboards. Treat the field as living background, not wallpaper. Because the river under our feet doesn't care about our deadlines. It moves on its schedule. Our margin depends on noticing when its breath gets shallow and acting before the next storm asks if we did. Reversal versus excursion, timelines and myths. Rocks don't do height, they do memory. Basalt flows cool and lock in the field's direction like millions of tiny compasses. Seafloor spreads and writes a barcode of flips. Lake mud and ice layer up annual pages that catch the quick swerves. Stack those witnesses and you get two tempos, reversals and excursions. Reversals are the long game. In the paleomagnetic record, full flips unwind over thousands of years. The neat dipole weakens, directions wander, multiple poles can show up at once, and eventually the polarity settles the other way. It's messy and slow on human terms. Your grandparents don't wake up to south where north was. Your great-great-grandchildren notice the outcome, not the turn. Excursions are the sharp detours. They're near flips that don't finish the job, centuries long, sometimes with decades where the field weakens fast and directions go weird, then snap back to the original polarity. The Lachamps excursion, about 41,000 years ago, is the cleanest example. Lava in France and New Zealand records wild bearings for a brief window. Ice cores show beryllium-10 spiking, a sign the shield strength fell to a small fraction of normal for a short time. Some reconstructions argue auroras marched toward lower latitudes. Ozone chemistry likely shifted. Climate nudged regionally. Humans were there, painting caves, wearing clothes, adapting. No mass die-off tied to magnetism, but the sky behaved differently, and that mattered. Stakes for us live in tempo. Civilization runs on decades. Airports, satellites, grids, finance. Those investments live 5 to 20 years at a time. A 1,000-year reversal does pressure. It doesn't slam. An excursion can line up with a lively solar cycle and turn the next 20 years into a stress test. You don't need a flip to feel it. A wobble on a weaker baseline means more satellite upsets, rougher GPS in a stirred ionosphere, more polar detours for radiation and comms, and higher geomagnetically induced currents heating transformers for the same solar punch. Now, the myths that keep messing up the brief. Myth 1, the field can vanish overnight. It can't. The geodynamo doesn't have a known off switch. Even during reversals and excursions, a field persists, messier, multipolar, weaker in spots, stronger in others, but not zero. Myth 2, a flip equals instant apocalypse. The fossil record doesn't show extinctions lining up with reversals. Life rides them out. The modern risk isn't biology, it's technology. Myth 3, the core stopped.
The best evidence says the inner core's rotation slowed relative to the mantle and may oscillate, with hints of slight backtracking and year-scale structure changes at its top. That's a variable gear, not a seized engine. Here's what the rocks tell us that should change behavior now. 1. Regional patchiness is normal during both reversals and excursions. That's the family tree the South Atlantic Anomaly belongs to. Weak here, strong there, shifting with the flows. 2. Direction can swing wildly in some places while barely budging in others. For navigation, that means treat the compass as context, not gospel, and keep the world magnetic model fresh, so software can reconcile magnetic and true. 3. The steepest parts of an excursion can bite within human plans. That's not a headline to panic over, it's a procurement note. Harden satellites for a rougher background, put GIC sensors on substations, build polar protocols that assume more frequent comm fades and radiation watches, teach the thresholds like weather. What nobody can give you, honestly, is a clock. Models can explore thresholds. Paleo records can show frequency bands. But no one can date a reversal's start or call an excursion a decade out. The responsible stance is scenario planning. If the South Atlantic Anomaly keeps spreading and deepening on recent trend lines, and if pole drift keeps forcing out of cycle model updates, what changes in the next 5 to 10 years of your systems? If it relaxes, what does that save? Set ranges, tie actions to thresholds. One more truth from Stone and Ice. Volatility is normal over centuries. What's not normal is our dependence on nanosecond timing and electrons in long lines. That's why this matters, even if no flip shows up this century. A weaker patch plus a busy sun equals more weeks, where satellites sleep longer, grids run hotter, planes detour, and timing drifts unless redundancy holds. You don't need doom to justify a checklist. You need receipts. And the rocks, the satellites, and the poles just handed them over. The fragility map. Satellites, grids, and planes. Lay the systems out like a map. Above us, through us, around us, and you'll see the same invisible hand pressing on different nerves. Start in orbit. Satellites don't fail dramatically, they fray. In a weaker patch like the South Atlantic Anomaly, high-energy protons slip lower and smack electronics that anywhere else would shrug. One hit flips a bit in memory. A watchdog catches it and corrects. Another hit lands in a timing register. A wheel spins when it shouldn't. Software drops to safe mode and waits. None of this is rare anymore over the South Atlantic. The expansion since 2014 turned a tidy no-go box into a moving shoreline. Operators respond with choreography. Power down sensitive detectors inside fresh masks, raise particle thresholds, schedule naps through the bite, and sprint outside it. Error-correcting memory, latch-up protection, selective shielding, they all matter. But every gram of shield steals delta V. Every defensive routine steals minutes. Duty cycles shrink. Data gaps widen. During a lively solar cycle, drag joins in, the thermosphere puffs, low-orbit birds lose altitude faster, and propellant burns creep forward on calendars. Missions still work, margins thin. And GPS, the quiet glue, feels it indirectly when storms stir the ionosphere, bending signals and adding jitter that timing receivers have to ride out. Parallel action on the ground, long wires listen to the sky, geomagnetic storms drive electric fields across continents. High voltage lines and pipelines act like antennas, pulling quasi-DC currents into big transformers. Cores heat, steel saturates, protection relays, see ghosts, reactive power swings, voltage sags. Operators know the drill. Block automatic capacitor switching. Hold voltage set points tighter. Bring extra spinning reserve online. Postpone maintenance on stress corridors, and be ready to island if the oscillations won't sit down. The difference in a patchier field is simple and cruel. The same storm pushes higher geomagnetically induced currents in the same places. Quiet erosion shows up as accelerated aging of transformers that take months to build and move. Loud nights show up as controlled load shedding to save the big steel. Timing rides this backbone. Cell towers and trading floors discipline their clocks to GPS. When ionospheric scintillation makes GPS ugly, good holdover clocks keep time for hours. If you cheaped out, drift creeps in and cascades into drop calls, desync packets, and system alarms you can't clear with a pep talk. Now the planes, the part of this story humans feel in their bones, Polar routes shave time and fuel, but they perch where space weather hits. Communications and radiation hardest. On an active day, high-frequency radio fades, SATCOM drops packets, dosimeters tick faster, airlines carry playbooks, pre-brief space weather advisories, detour south when blackout risk rises, adjust altitudes, add fuel, and rotate crews. Those choices cost money and time, and they land on weeks when everything else is already wobbling. On routine days, magnetic drift is paperwork. Runway renumberings, fresh procedures, updated models loaded into FMS so heading references agree with the new paint. On noisy days, drift plus a storm means dispatchers rewriting tracks mid-shift, pilots juggling comm handoffs, and maintenance chiefs double-checking databases against WMM updates, because a half degree out of sync on a low ceiling day is the kind of nonsense that steals margins at the worst moment. Thread a micro story through all three. A storm window opens on a Thursday. In orbit, a weather bird spends extra minutes in the South Atlantic Bight because the weak lobe near Africa deepened again. Safe mode scripts fire early, late, twice. Flood maps arrive after the crest. On the ground, GIC sensors at a substation nudge past thresholds. The operator blocks auto-switching, calls for more reserve, and sheds industrial load for 2 hours to keep a known weak transformer from cooking. In the sky, 2 polar flights divert, burn extra fuel, and land late. Connections evaporate. Crew duty times get tight. No one headline, just friction. Data late, electrons hot, airplanes south, stacked into a day that didn't need help being hard. Insurers notice before the public does. Satellite policies carve out exposure over the South Atlantic more explicitly. Deductibles creep up unless you can show mitigation. Shielding grams, error correction rates, updated SAA masks. Reinsurers build geomagnetic variables into catastrophe models for utilities. Bond markets price grid hardening and spares differently for regions that light up magnetometers. Aviation underwriters nudge premiums when polar detours become routine. Money is a seismograph. It registers tremors in operational.
Logs long before press offices do. Here's the fragility map in one line. Anywhere codes ride on precision, and electrons ride in long lines. A wobblier shield turns routine storms into bigger chores. Satellites cope with armor and choreography, but their lifetimes and duty cycles tilt. Grids cope with sensors, procedures, and spares, but their weakest links warm faster under the same punch. Planes cope with playbooks, but costs and doses climb in bad weeks. Stack them, and you don't get cinematic collapse. You get cascading inconveniences that on the wrong Thursday turn into real outages. The fix isn't panic, it's rhythm. Dashboards, thresholds, drills, and paying the small costs now so the big ones don't all arrive on the same day.